Why does a simple, sad song give you literal goosebumps? Or why does your brain lock onto a catchy rhythm? Welcome to S Says Psych. Today, we are exploring the neurobiology behind the songs we love. We will break down the ancient survival mechanisms that drive our musical taste, the specific neurochemistry triggered by a beat, and the biological reasons we seek out heartbreak anthems. This is a new channel. Please subscribe and like to show support for this content. For evolutionary biology, music poses a formidable paradox. Unlike food or shelter, singing and drumming offer no obvious advantage for physical survival. Charles Darwin famously noted that the human capacity for musical notes serves no direct use in reference to the ordinary habits of daily life. To understand why we kept this trait, we have to look at ancestral primate societies. Social cohesion was originally maintained through physical grooming. But as hominid groups grew larger to defend against predators, the time required to groom every social partner exceeded the hours in a day. This created a bonding gap that threatened the stability of the tribe. The music and social bonding hypothesis suggests that music evolved to fill this gap. It functioned as vocal grooming, allowing dozens of individuals to synchronize their psychological and physiological states simultaneously through shared sound and rhythm. This drive for rhythm is linked to bipedalism. Walking on two legs produces regular, predictable acoustic signals. Early humans developed the ability to entrain or synchronize to a pulse, allowing a group to walk in perfect step. By masking their own footsteps, they created periods of relative silence that made it easier to detect stalking predators. This shared rhythmic exertion triggers the endogenous opioid system. Participating in synchronized dance or choral singing releases endorphins into the central nervous system. These neurochemicals increase pain thresholds and generate a sense of euphoria, forging the non-kinship bonds necessary for a large-scale society to function. Music is a specifically adapted biological technology. It was engineered to dissolve the cognitive boundaries between the individual and the group, turning a collection of people into a single cohesive unit. In a modern context, our brains still treat abstract variations in air pressure as a primary reward, translating sequences of sound into intense neurochemical hits. This reward cycle happens in two phases. During the anticipation phase, when you expect a melody to resolve or a beat to drop, your brain releases dopamine in the caudate nucleus. This region is linked to our predictive systems, essentially rewarding the brain for forecasting what comes next. When that musical climax finally occurs, the dopamine release shifts to the nucleus accumbens. This is the core of the limbic system, responsible for the intense emotional arousal we feel during the most powerful moments of a song. We know this link is causal because of pharmacological studies. When subjects are giving Levodopa to boost their dopamine levels, their physical response to music increases. They experience more frequent chills. When those same receptors are blocked with Risperidone, the subjective pleasure of music is significantly attenuated. We derive pleasure from these sounds because our brain processes musical syntax through Bayesian predictive coding. It treats a song like an acoustic puzzle, generating top-down predictions about the melody. When a composer violates those expectations with a surprising note, it creates a prediction error that keeps the brain engaged. This graph illustrates the sweet spot of musical pleasure. If a rhythm is too predictable, it offers no new information. If it's too chaotic, the brain can't find a pattern.
Aesthetic pleasure and the sensation of groove peak at moderate complexity, where the music is stable enough to follow, but introduces enough syncopation to keep the reward system active. Musical emotion is the result of this constant cycle, the brain's drive to make predictions, and the intense reward that follows when those predictions are playfully violated. These preferences start at the lowest level of our sensory hardware. In the auditory brainstem, consonant intervals like a perfect fifth create simple integer ratio frequencies. These waveforms allow for highly efficient periodic neural firing, which our brains perceive as stable and pleasant. Dissonant intervals possess complex mathematical ratios. The auditory system processes these aperiodic signals inefficiently, leading to chaotic neural firing and cognitive friction. This is why we instinctively feel that a discordant chord needs to resolve into a simpler one. If we are biologically wired to prefer pleasant, predictable stimuli, we face the tragedy paradox. Why do humans actively seek out and derive pleasure from music that evokes sadness and grief? For years, researchers pointed to the prolactin theory, claiming sad music tricks the body into releasing soothing nursing hormones. Recent studies have dismantled this idea, finding no increase in prolactin levels when people listen to sad compositions. The actual reward comes from oxytocin. In listeners with high trait empathy, sad music triggers a sense of being moved. Because we are in a safe environment, protected by aesthetic distance, we can engage with these intense emotions without experiencing real-world distress. Sad music functions as an empathetic virtual agent. It acts as a surrogate for social support, simulating human connection and helping us regulate our moods during periods of isolation. Beyond immediate emotion, music acts as a scaffold for our long-term memory. The medial prefrontal cortex links musical tonality directly to self-referential information. This overlap creates the reminiscence bump, the tendency for adults to have a disproportionately vivid, emotional connection to music heard between the ages of 15 and 25, when their self-identity is forming. Human cultures build architectural frameworks to harness these biological realities. We see this in the Indian classical tradition, which has spent 2 millennia formalizing the link between sound and emotion. This tradition is rooted in rasa theory. It suggests that while real-world emotions can be chaotic or painful, artistic expression transmutes them into rasa, a refined, universalized aesthetic essence. By following a precise formula of melodic notes and physical expression, performers guide the audience toward a shared, empathetic experience. In modern India, composers like A.R. Rahman have updated this by blending classical raga structures with global orchestration. This hybrid music serves as the dominant soundtrack for the subcontinent's most important social rituals, from weddings to national festivals. Because these complex musical structures are rehearsed and repeated during the peak of a person's developmental reminiscence bump, they become permanently anchored to their sense of identity. While our neurobiology dictates how we process a beat, culture dictates what that beat means. By bridging ancient classical motifs with modern pop, these sounds move from being a survival tool to a primary mechanism for intergenerational memory. Why does a simple sad song give you goosebumps? Or why does your brain lock on to a catchy rhythm? We've seen how music is a bridge between our ancient evolutionary past and our complex cultural present. It synchronizes our groups, rewards our predictions, and anchors our memories. This is a new channel. If you enjoyed this deep dive, please subscribe and like to support more content on the psychology of our daily lives.